Okay. Hello everyone. This video I'm going to show you 8 example for shear moment diagram. Okay. And just wait for me for a moment. Pick up. Want to pick up my notes. Yep. Sorry, I want to pick up my notes. Okay. And this I'm going to draw a shear moment diagram, and it's a very simple one. But for the shear moment diagram, I think you need more demonstration drawing the shear moment diagram because you haven't drawn such diagram before. Okay, and previously we have shown some examples. Okay, and this one is kind of easy one. This one is a kind of easy one. Okay, so let us see. Okay, so this is a beam, and A is a roller support, B is a roller support, and A is a pin support. Okay, and there's an external loading. Okay, external loading acting on the beam, and there's also external moment, or external torque apply on the beam, apply on the beam. And okay, so this could give a geometry information, and then okay, draw a shear moment diagram of the beam. Okay, so in the previous example, I just tell you that if you want to draw a shear moment diagram, first of all, you need to do the rigid body equilibrium first. Okay, do the rigid body equilibrium first. Okay, so let's do the rigid body equilibrium first. Okay, so we know that A is a pin support and B is a roller support. Okay, so let's draw the first of all, draw a free body diagram of the beam. Okay, free body diagram of the beam. Okay, here. Okay, and okay, so A is a pin support, so there's only a reaction force. I call it AY here, and AX, and B is a roller support. Roller support, we have only a reaction force point up. Okay, and okay, what's our external loading? External loading, okay, it's acting as here, it's 800 Newton. Here is 600 Newton, and here is the clockwise moment, 120, 1200 Newton times meter is Newton. Newton. Okay, so and this maybe it's not in right scale, but it's just a scheme. Okay, just a simple repetition of this problem. Okay. Okay, so first of all, let us calculate the reaction force from the support. Okay, so use the rigid body equilibrium. And okay, first of all, summation of x equal to 0. So I think you will have ax equal to 0. That's mean x equal to 0. Okay, but this is not very useful. Okay, and then all y component for summation, all y component for equal to 0. So here's ay minus 800, and it's a moment we can only right now we care the force. Okay, the force and minus 600, and we had by, and overall is equal to 0. Okay, so and ay plus by equal to 1400. Okay, so can we solve ay and by this equation? Of course not. Okay, because one equation, two unknown, we cannot solve it. And so we need another equation, so we use the total moment of the system is a total moment of the system is 0. So and we choose A as a reference point. So okay, let's see. This force will create a moment with respect to A point. Okay, I would say this is a B point. This is A point. Okay, and this will generate clockwise rotation. Clockwise rotation. So it's a negative. So negative 800 times its labor arm. And here we have a moment. External moment is also counter. It's also clockwise. It's also clockwise. So minus 1200. And this is also this force also create a moment with respect to A, and it's also clockwise. So minus 600 times 1, 2, 3. Yeah, 3. And or force B create a moment with respect to A, and it's counterclockwise, so it's plus by. And don't forget its labor arm 1, 2, 3, 4. So labor arm is 4 and it's 0. So let's us see. Okay. So what's the value? Minus 20,000, 38,000 plus 4by is 0. Okay, so the by is I'm just checking my answer. So what's the by? Yeah, I think it's right. So By is 950 is Newton. Okay, if you have a By and Ay plus By is 1400, so you will get the Ay is equal to 450. A unit is Newton. Okay, so with this information, we can start to draw a so-called shear diagram. We draw a shear diagram for first. Okay, for shear moment diagram, we always draw a shear diagram first. And I need more space, so maybe I clean this up. Okay, so start from yeah, it's very hard to draw a straight line in the head. Okay. So let's start with here. So this is the X and this is shear. It's external shear. Yeah, I keep saying that the shear moment diagram actually is external shear and internal moment diagram. Okay. And we start from the point A. Okay, we start from point A. We start from point A. Okay. And at A point, we have 450 Newton. Be careful. At A point A, we have 450 Newton at A point. 450 Newton. So we start from here. Okay, here's 450. Okay, and we keep moving to the right. Okay, between 0 and 1. So I so call it 1. Between 0 and 1, there is no external force. Right? Between 0 and 1, there is no external force. So we will keep 450. Keep 450. But at the position 1 meter, we will subject to the 800 Newton point down. We subject to 800 Newton point down. So we will have so at the position 1 we will have the 450 and minus 800, so we will have minus 350 Newton. So at the position 1 we will have let's check maybe just right here 350. 350. Okay, this is 1. And so let's keep moving for between 1 to 2 and 1 to 3. 1 to 3, there is no external force. So this is 2, this is 3. So it looks like we don't have any external force between 1 and 3. Okay, so that's the so we'll keep minus 350. And at position 3, we'll have external force 600 Newton and it's point down. So at position 3, okay, we'll have the okay, maybe actually here we'll have at position 3 we have minus 350 and we have 600 Newton point down, so minus 600. So we will have minus 950. So okay, let's see. Maybe it's probably 900 minus 500, 9 minus 950. So there is here minus 950. So okay, and between 3 and 4, do we have any external loading? Looks like not. So we keep minus 950. We keep 950 at that. Okay. So between 3 and 4, we don't have any external moment, so we keep minus 950. Okay, so at this point 4, okay, you see it's not a coincidence. At the point B, we have a reaction mode and reaction force 950 point up. So that means we will back to 0. we will back to zero. Okay, so let's draw a solid line. Solid line. We will back to zero. Okay, that's very important. We here we'll back to zero. Back to zero. Okay, that's very good checkpoint. Okay, so just like no matter it's shear diagram or moment diagram, you must be back to zero. Okay, that means your system is at the rigid body equilibrium, so you must be back to zero. You see here, this point is minus 950, but we have a reaction force 950 Newton plus. So you are back to zero. That's very important. Okay, so that's a shear diagram. Okay, and then we will have another, it's called moment diagram. So let me see, moment diagram. So let's draw another. Okay, let's start with the moment diagram. I think, okay, maybe it's good. Yeah, we still start from the A point first. A point first. Okay. So the moment diagram, you just keep in mind. So the change of the moment equal to the area under the area under the shear diagram. Changing of the moment equal to the the area under the shear diagram. So let's yeah, we still from we're drawing to 0 to 1. Okay, 0 to 1. Okay, 0 to 1. It start from 0. So what's the so let's calculate what's the area one. What's the area here? The area here is 450 and times the 1. Okay, so the change of the moment equal to the area under the shear diagram. So the area of this part 0 to 1 is 450. So that means we change is from 0 to 450. So this must be 450, and we change 0 to here, and it's steady change or increasingly change. Is the change is look like this, or look like this, or steady, or look like this. Which one? Which one? Okay, that's because it's rectangular shape. If the rectangular shape, I keep saying that the rectangular shape, if you cut the slice, if you cut slice, maybe that's very accurate. If you cut the area with dx, with the width dx, you will see the height is the same. The height is the same. Okay, that means the area, each tiny area is the same. That means the change. Means the change is the same. That means the slope is the same. Okay, so you will see dm over dx is v. Okay, so the moment so the shear is constant, so that means the dm dx is a constant. Okay, you can think also in this way. Okay, the shear here is constant, so that means dm dx is constant, so it must be a straight line. Okay, simple straight line. So it will look like this. So it's right here. Okay, this is one. Okay, so and let's moving from 1 to 2. Okay, 1 to 2. Okay, 1 to 2. Okay, 1 to 2. Okay, let's see. 1 to 2. Okay, wrong color. 1 to 2. 1 to 2. It's 1 to 2. Let's see. 1 to 2. What's the area here? 1 to 2. What's the area here? It's a minus 500, 5 minus 350, and times 1. So okay, so area 2 is minus. So we will change. This is 2 here. Okay. So what's the area for area 2? The area 2 is minus 350 times 1. So minus 350. Okay, so the area 2 is minus 350. So the change must be minus 350. So we have 450 at point 1, and we'll have a change of 350. That means at point 2, we will switch to here. We will change to 100. Okay, this point is 100. And also rectangular area, so it must be a steady decrease. Okay, at this point 2, at position 2. But there's but at the position two, yeah, don't forget the position two. We have this at the position we have applied a 1200 Newton, 1200 external moment at the position two. Okay, but 1200 this is external. At position two, we have external moment, ex moment. 1200, 1200, and it's clockwise. Clockwise means negative. So at the position two, we have external moment minus 1200. That means we have internal moment. We have internal moment 1200. Okay, so I keep saying that this moment, the shear moment diagram, the moment is internal moment, and this is external shear. External shear. I keep saying that external shear and internal moment diagram. So external moment is minus 1200. Okay, so that means internal moment is positive 1200. So at this position two, we'll have add 1200. So here we'll have the value here is I think, yeah, maybe it's not a scale, but this will be this will be this will be 1300. Okay. And then, okay, so this position two, okay, we move it to the position three, okay, position three, okay, position two to position three, okay, let's us see. This is area three, okay. What's the area for area three? What's the area for area three? For area three is minus 350 times. Okay, just it's also minus 350. So at position three, we have changed on minus 350, and it changed from the 1300 1300. So at the position three, the value will be, I think the value will be minus 950. Okay, it must be. So it's 1300 changed to the 950 because it's 1300 minus 350 equal to 950. Okay, see the logic here. So actually this is minus 350. Okay, so and then it's also rectangular shape, so it must be a steady change. Must be a steady change. Should I do it? Maybe I cover solid line here. Okay, so, and then from the three to four. Okay, from three to four. Three to four is this here. Three four is here. And what's the area for the area four? Four is here. What's the area for area four? Area four. Let's see. Area four. Area four. Let's see. Area four. It's 900 minus 950 and times the one. So it's minus 950. So it will change. The change will be 900 minus 950. So it starts the change from 950. So you will see we will back to zero again. Back to zero again. So we will draw, and it's a rectangular area, so it must be a steady change. A steady change. The slope is a constant. Okay, here. Yeah, you will see we are back to zero again. That means we are drawing the right. We are drawing the correct moment that it must be back to zero. That means you are in system in rigid body equilibrium. Yeah, back to zero. Yeah, back to zero. Okay. Okay, so here is the shear moment diagram of this being subject to this external load and external moment. Okay, so yes, also takes some time. Even if it is a very simple example, it still takes some time. Okay, so I just start a video here. Okay, you need to. I hope you can do practice of this shear moment diagram. Okay, see you in another video. Okay, bye bye.